This video continues going through the summer worksheet for Precalculus review. It does cover, as you can see, Roman numerals 3, 4, 5, and 6. Despite that, it is still shorter than the first video was, covering Roman numerals 1 and 2. There is also a third video that talks about what's in Roman numeral 7. In calculus, you're not going to be quizzed on the trigonometric values like you were in precalculus, but it is important to, when you need a value, to be able to think of what it is. And on the AP test, they will occasionally ask you for a trig value. Most of the time, I tell students, most of the time they ask for one of these on the axes, like either at 0 or at pi over 2 or over here at pi. But at the very least, you need to know the first quadrant, okay, and then be able to, count your way over to another angle. Like if I needed, 4 pi over 3, I could say, well, here's pi over 3, I know is 60 degrees. Another 60 degrees gets me to 2 pi over 3. Another 60 degrees is 3 pi over 3, which is just pi. And then another 60 degrees is 4 pi over 3. So I could fairly quickly figure out that the angle is down here. Here's 4 pi over 3. And then I would know that, the two numbers that go with the sine and the cosine values that go with that point are going to be along the lines of the 1/2 and the root 3 over 2. So I just need to figure out, which one's which and whether I need negatives or positives. So looks to me like with the symmetry of the circle, I would have negative 1/2 for the x-coordinate and negative root 3 over 2 for the y-coordinate. Therefore, the cosine of 4 pi over 3 is simply negative 1/2, right, the x-coordinate, and the sine of 4 pi over 3 is negative root 3 over 2. And of course, if I needed to find the tangent or the cotangent, it's just some combination of these two numbers, whether I'm dividing, and then we also have the secant and the cosecant. So the cosecant of 4 pi over 3 would just be the reciprocal of the sine, right? So it'd just be negative 2 over root 3. So that's the the kind of facility you need to have with the unit circle and being able to find trig values. The next little exercise in part B of, let's see, this is Roman numeral 3, is really just kind of combining what we've talked about with the identities and combining that with your knowledge of just the basic right triangle trig, or the SOHCAHTOA. I think you'll get the hang of it once you see me do a couple of examples. And I did try to pick the simplest examples. One very simple example here would just be, what's the cosine of theta? Well, the cosine of theta, of course, is just going to be the adjacent leg, which is x, over the hypotenuse, which is 1. If I ask what's the sine of theta, well then we need to know what the opposite leg is over here. So to get that, we're just going to use Pythagorean theorem, right? Since we know two sides of the right triangle, then we know this side over here is going to have to be, see if you know your Pythagorean arithmetic, but it would just be the square root of 1 minus x squared, right? If you think about it, you would say that x squared plus y squared equals 1, so therefore if you solve for y, and if we let this be y, solving for y would give you the square root of 1 minus x squared, so that means the sine of theta would be the square root of 1 minus x squared over 1. So what does that mean the cosecant of pi over 2 minus theta is? Now that might seem a little tricky. Keep in mind, the pi over 2 minus theta, that's just your angle, okay? And that would be the same thing as if I asked you, if I had said it was the 90 degrees minus theta. Pi over 2 is, in radians, is 90 degrees. So if this is theta down here in the drawing, then of course pi over 2 minus theta is simply this angle right here, okay? So what is its cosecant? Well, since we know the cosecant is the reciprocal of sine, let's figure out what its sine is. So the sine of pi over 2 minus theta, let's see, I believe is the opposite leg from that angle, which would be x over 1. So therefore the cosecant must be just 1 over x, right? It's reciprocal. So that's not too bad, just a little sneaky with the angle. All right, now how about the sine of 2 theta? Well, there we go. There's a double angle, so we need to use one of our double angle identities here. And we know the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. So we would have 2. We've already figured out the sine of theta is the square root of 1 minus x squared. And we know the cosine of theta is just x. So there's really not a whole lot you can do with that expression, but we could rewrite it as, say, 2x times the square root of 1 minus x squared. All right, that's really all there is to this. It's really just using SOHCAHTOA. But notice what we're able to do is take a trig expression and rewrite it in terms of just a variable x. See, there's no trig over here, so that's kind of nice. It lets us take something that's transcendental, okay, like a trig function, and rewrite it using a function that's not transcendental, or an expression that's not transcendental. It's very important to be able to work with functions in general without necessarily working specifically with one type of function. So in Roman numeral 4 here, parts A and B, we're going to be just taking a look at some function g of x. We don't know exactly what it is. Maybe it's a polynomial or transformation of a power function, but that's not really the point. We don't know its formula. We just have the graph, and we want to answer some questions just using the information from the graph. So you can see that, as it says, each of these answers should be just in terms of A, B, C, P, Q, or R. And these A, B, C, P, Q, or R, these are just numbers that are on our graph, on the axes of our graph. We can see the P, the R, and the Q are X values, and the A, B, and the C are Y values. This exercise also helps us gain a better knowledge of function notation and what it exactly means. So looking at the first part, we just want to figure out, what does g of q equal? All right. Now, of course, g is our function, and we see that q is an x value, or a value on the x-coordinate. So what would that mean g of q is? Well, the idea is we're taking this number q and plugging it into our function g, and of course that would give us back some output value. So if you look at the graph, we could label this point right here, which corresponds with x-coordinate of q. It has an x-coordinate of q, and what is its y-coordinate? Well, its y-coordinate is g of q. Okay, in other words, the y-coordinate is the value you get after you plug q into g. So we could label this point in two ways. We could label it q, g of q. We could also label it as q comma c, because we see that c is the y value at that point. So that must mean that g of q equals c. Hopefully that's what you were thinking, but if not, there we go. I just did the first one for you. So see if you can do items 2 and 3, and then check your answers in the back with the answer key. Taking a look at Roman numeral 4, this is one that usually causes students to have some questions. We've kind of understand that what g of q or g of some number gives us, but what about g inverse? We need to keep in mind that we're not actually looking at the function g inverse. We're looking at the function g. But there's one thing that we really should remember from precalculus about inverses. All right? And that is that when you get the inverse of a function like g, what you are doing is you are switching the input and the output, or you're switching the domain and the range, or you're switching the x's and the y's. Everything gets switched. And we'll see this in another exercise later on, or a few other exercises later on. But the idea is that if B is an input value for G inverse, that means it must be the output value for G. All right. So if we can find the point on the function G that has an output value of B, then we should be able to figure out what goes in the blank here. And hopefully you've already located this point. Right here it looks like this is the point on G that has an output value of B. We could, of course, label this point as the point PB, P comma B. All right. Well, if P comma B is on the function G, and we know that inverses simply switch the inputs and the outputs, then that must mean that the point B comma P is on G inverse. Which means that if we were to plug B into G inverse, that would mean we have to get back P, right? So, of course, now I've given you this answer. It is just going to be P. Even though we're not looking at G inverse, we know a lot about G inverse because we know a lot about G. And whatever we find out about G, we're simply going to switch it or flip it around, and then we know about that point on G inverse. Now that we've had this discussion about this problem, I'd like you to finish, do part B on your own and check your answers in the back of the sheet. Given what we just talked about on the previous slide, I'm not even going to say anything about part 1 here of part C in Roman numeral 4. You should be able to answer that question. Of course, I've given you information about F right here. As far as items 2 and 3 are concerned, we need to make sure we understand what the difference is between an odd function and an even function. Of course, many pre-calc students remember that it has something to do with symmetry, and that an even function is symmetric with respect to the y-axis. An easy way to remember that is that, one reason we call it an even function is that any power function with an even number power has that symmetry with respect to the y-axis, so like y equals x squared. And then as far as an odd function goes, if you have something like y equals x cubed with an odd power, then we have symmetry with respect to the origin. What that means graphically also is that if the point AB is on the graph of an even function, then the point negative A positive B is also on the graph. And when it comes to symmetry with respect to the origin, if the point AB is on the graph, then the point negative A negative B also has to be on the graph. And that also plays out in our definitions. We can see that if we replace the x value with a negative x, then we will end up with the same y. So f of x equals f of negative x. And when it comes to the odd function, you have to replace both the x and the y with negatives, and once you do that, you will have the same formula. And so that's why f of x equals negative f of negative x. With that information, why don't you go ahead and answer this question and check it in the back. Of course, it's very important to pay attention to the instructions, after the commas here, because that dictates which piece of the formula you're going to be plugging numbers into. Just to kind of get warmed up, let's do the first one together. So if we have to figure out h of negative 2, then of course we're plugging negative 2 into our formula, and when we look at the instructions, it does appear that when x is equal to negative 2, we're not actually going to get an answer back. I don't want to plug it in up here because that's for just x less than negative 2, and I don't want to plug it in down here because that's just for x greater than or equal to 0. So all we can say about h of negative 2 is that it is undefined. I will mention that with item 4 here, it's very easy to determine the domain of a piecewise defined function because it's actually already determined for you up here. But when it comes to determining the range, of course you're looking at what are all the output values or what are all the y values you get back in the function. So I strongly recommend that you sketch h's graph first, and I really think you should be able to do that without using a graphing calculator. A little later in these on this sheet, this packet, you're going to be working with transformations. Now, of course, the top piece here is linear, and you know what some students will do on this is they will just go ahead and graph the entire line. So if we know it's got a y-intercept of -4 and it's got a slope of -2, then it's going to be going down like this. And I believe if we plug in -2 in here, we're going to have +4 -4, so our x-intercept is actually at -2. And so then once you've sketched that, then what you want to do, of course, is take away the part that you don't want. And the part we don't want is all values that are greater than or equal to -2. So we could come along with our eraser now and kind of erase off that piece there. And let's see, I also don't want to include that point. So we're looking at an unshaded circle right there. Now, as far as the rest of the graph goes for x values greater than or equal to 0, I challenge you to see if you can figure out what this graph will look like. Of course, it's just a parabola, but just by reading the transformations. We'll get more practice with that a little later on in the packet, but this is written so that you can read the transformations easily. If you're not sure about how to do that, then you know, another way you can graph it, of course, without having go into your calculator would be just to plug some points in. Plug some x values in, get back the y's, and then plot your points. And that would not be hard to do here. So see what you can do with that, and then once you have the graph, you should be able to determine all the y values that come off that graph. The last part of Roman numeral 4 refers to something that we can do to any kind of function, for the most part, and that is to determine its inverse. Or in other words, we can invert a function. And remember, we were saying earlier that inverse functions are functions for which the domains and the ranges are switched, or the inputs and the outputs are switched. And that's all we want to do here algebraically to get a formula for the inverse function. Right now, the x is my input variable and the y is my output variable. So all I'm going to do is to solve this equation for x. I know the last thing I want to have is x equals, and then I'll have something down here in terms of y. That is my goal. And then you see we will have the x coordinate, the x variable as the output and the y variable as the input. So to do that, of course, it's going to require some algebra skills. If we're trying to get the x by itself, then let's get rid of everything else that is around it. And we want to do this, of course, from the outside in. So just like you would take off your shoe before you take off your sock, we want to get rid of that +2, right? So let's subtract the 2 over to the other side. We'll have y minus 2 equals the natural log of the x minus 1. And now the next layer to get rid of is that natural log. How do we get rid of natural logs? Well, we were working on this earlier, right? In the packet, we need to change it to an exponent. The way you undo logs is by using its inverse, which is the exponential, or e raised to some power. So let's change this to an exponent. We know our base is e down here, so we would have e raised to the y minus 2, right, equals x minus 1. And now all we have to do is add the 1 over. So we will have e to the y minus 2 in the exponent, and then plus 1 after the exponent equals x. And as far as I'm concerned, we can leave the formula looking like this. I know you're used to seeing formulas as y equals, but if this was a function, let's say x represented the number of, say, the area of a wall space that you wanted to paint, and y represented the number of cans of paint you were going to use, then if we get the inverse, we would want the y, which represents the number of cans, to be the independent variable, and the x, which represents the wall's area, to be our dependent variable. So I'm always hesitant to switch the x and the y unless I'm going to graph the formula on a calculator, right? If I need to graph it on a calculator, then yes, I have to actually write it as y equals e to the x minus 2 plus 1. But if you want to think of it, this formula up here is simply f inverse of y, while this formula is f inverse of x. They're the same function, just a matter of which variable you want to use. The example over on the right is we're going to do the same thing. It just gets a little trickier algebraically. But you've actually already solved a problem like this earlier in the packet. Of course, we're trying to solve for x, so and get it same way as we had before, x equals something. So as far as I'm concerned, the easiest thing first of all to do is let's get rid of that denominator. Let's stop having a fraction in here. So we're going to multiply over both sides by the 11 minus 2x, so we'll have y times 11 minus 2x equals x plus 3. And now the only thing we can do next, I guess we could divide back, but then we'd be where we started from. But the only thing we can do next really is distribute that y. So we'll have 11y minus 2yx equals x plus 3. And remember, we're trying to solve for x. So this is one of those situations that we saw before where we just need, it's really a linear equation in terms of x. So what we need to do is get all the x's on one side and get everything else on the other. So I'm going to subtract the 3 over to the left side. So we'll have 11y minus 3 equals, and we'll add the 2yx over to the right side, and so we have 2yx plus x. And now that we have all the x's on the same side, yes, hopefully you're thinking what I'm thinking, we can just factor that x out. We're left with 2y plus 1, and then that equals 11y minus 3, and then we simply divide, and we have x equal to 11y minus 3 divided by 2y plus 1. Really not that difficult once you get used to it. And really the key was, all we really could do at the very beginning was get that denominator. Let's not work with the fractions. Let's just multiply over, and then we can get our x's on the same side. So now we get to part 5, which deals with transformations of functions. And it's quite important to be able to quickly visualize what a graph is going to look like based on the transformations that you might read of some parent function such as y equals x squared. Of course, it should make sense that shifts have to do with adding and subtracting numbers. Reflections are when you have negatives involved, and then stretches. Those stretches or compressions occur when you multiply by some factor. All right, and as you look at it, all the vertical transformations being applied here are being applied after the function or outside the function. So if you apply transformations outside the function, then it's going to be a vertical effect on the graph. And if you apply a transformation to the x part or inside the function, then it is going to end up being a horizontal transformation. And one other important thing to remember is that horizontal transformations always go the opposite of the way they look. So if you see formulas such as y equals x minus 2 squared, we can see that it is being applied horizontally because we're subtracting the 2 from the x. It's not happening outside the square. And since it's a minus, you would think that means you go left, but horizontal transformations go the opposite, so you're really shifting this graph to the right. I know that seems a little confusing, but hopefully you covered the why of that in pre-calc. So in these exercises, I've given you a function f, and what you are to do is to graph the new function that's formed by applying some transformation. So if, let's say we had a new function, we'll call it g of x, and that was equal to f of, how about we say, 1/2 x. All right. Now, we need to graph g, so what we might look at first of all is the fact that we're multiplying the x part by 1/2. So we know that's going to be a stretch or compression. Multiplying by 1/2 would make us think that it's going to be a compression that will actually shrink in by a factor of 1/2. But remember, horizontal transformations go the opposite. So what that really is telling us is that there's going to be a horizontal stretch. And it's not by a factor of 1/2, because multiplying things by 1/2 would compress them, but it's by a factor of, yes, you guessed it, 2, okay, by the reciprocal of what you're seeing. All right, so that means we're literally going to multiply each of the x coordinates on our graph by 2. So let's see, if we come down to this, let's just use these guide points. Looking at the first guide point here on the left, my x coordinate is -3, and if I multiply that by 2, I will be out at -6. So we're not going to do anything to the y, but we're going to change the x value by multiplying by 2. If we do the same thing to the next point, yes, we will be out at -2 right here. At the next point, 0 times 2 is still 0, so that stays there. That's what kind of creates the stretching effect, because anything with a 0 is going to stay where it is. With the next point, 2 times 2 gives us 4, and then the last point on the right, 3 times 2 gives us 6. So now we can connect our dots, and we end up with a graph that looks like this. Not a great drawing job. It's a little hard to do on the computer, but the whole idea is to get those guide points done and then connect them with your pencil. Why don't you give this next one a try? See if you got this for your answer. Yes, well, looking at it, I know it's going to be a vertical transformation, and a -2 tells me to shift down 2 units, so all I did was subtract 2 from each of the guide points, and we have our graph shifted down 2. I threw a couple of non-traditional problems in there. I see one of the ones you have is the absolute value of f of x, which if you think about it, all that means is you're taking every y value that you get back and you're just making it positive. So if you can do that to this graph, then you should have it. And then I also gave you f of the absolute value of x. What can I say there? It just means, there shouldn't be any change if you plug in a positive number for x. Like if I plug in 2, or let's say I plug in 3, absolute value of 3 is still 3, and f of 3 is still 1, so that point wouldn't change. None of these points on the right are going to change. But now the ones on the left, when I plug in a -1 and take its absolute value, I'm going to end up with f of 1. So if I can figure out what f of 1 is over here from my graph, then that's going to be the output value for when I plug -1 into my function. All right, it'll be kind of a neat graph, and of course you can check it in the back. And then the last one I have you do is f inverse of x. Well, we've already talked about how you get an inverse, that you switch the input and the output, you switch the x's and the y's. So think about that. If you know that the point -1, +2 is on the graph of f, then that means you also know a point that's on the graph of f inverse, right? -1, +2 means I'm going to have +2, -1, right, on my new graph. So use that to help you get the inverse of f. I'm not going to promise that it'll necessarily be a function. You might be surprised to find out that you're going to be writing equations of linear functions fairly often in calculus. It happens a lot when we work with tangent lines. So I'm going to really be encouraging that you learn that you use the point-slope form of a linear equation. And it looks, of course, like this. It's much easier or quicker to write this than it is to write y equals mx plus b, because there's no computation to do with the point-slope form. I'm going to make one little suggestion that so that it's easier to plug it into our calculators, that we get used to writing it this way, as y equals m times x minus x sub 1 and then plus y sub 1. You see, as long as I know the slope and one point on the line, which quite often we will know, all I have to do is plug those numbers in. It'll just be y equals 1/2 times x minus 1 plus negative 7. And you'll probably get even quicker where you'll just automatically write as y equals 1/2 times x minus 1 minus 7. Did you see how quickly I wrote that? I didn't have to compute what the b value was. I just filled in my numbers and I was done. And if I want to graph this equation, it's also easy, because all I'm going to do is take the line y equals 1/2 x right here, and I'm simply going to shift it. All right, of course, y equals 1/2 x has a slope of 1/2, goes through the origin. And now when I look at my formula, minus 1 to the x means I shift to the right 1 unit. Minus 7 outside the x part of the function means I go down 7. So I'm just going to go down here to the point 1, negative 7, and draw in my line that has a slope of 1/2. Whoops, that should be parallel, but you get the idea. And I'm done. Part B of number 6 deals with equations of polynomials, and we can see that the information that we're given in the graph are the zeros of the function, as well as one other point here at 212. And because we know the zeros, that means that factored form is the way we want to approach this. And factored form of any polynomial is always written as f of x equals some constant times x minus z sub 1, 0 z sub 1 times x minus 0 z sub 2 times x minus 0 z sub 3, and so on. One of the things you do need to be careful about is when you have a multiple 0 at some location. And that happens anytime you take a graph that might normally look like this, and the two zeros that you have right there come together, then you end up having just one 0. Whoops. What I mean is for the graph to touch the x-axis and go back. So there's just the one point right here where it touches the x-axis. That's what you call a double 0 or a double root. And when that happens, you have to do something different with a factor. It would mean, like, if I have that, let's say that's happening at negative 3, then it would be x minus negative 3 and then squared. Because basically it's two factors that have kind of come together and become the same factor, or two zeros. All right. You can also, of course, have a triple 0 if you have a situation where three zeros come together. It would look something like what happens with the cubic function, where you have the two curves, but all three of these zeros come together and it only crosses the x-axis at one place. So, that factor would maybe look like say x minus 5 cubed, something like that. So be careful about that. And then the last thing you need to worry about with this problem is making sure you have the right k value. And that's where this point here, 2, 12, comes into play. All right, it should be fairly easy to figure out what all the x minus z's are. Once you have that, you're going to have to use that point to help you figure out what k is going to be in this formula. For part C of number 6 here, it's basic input, output things. You just have to be careful about making sure that that you're plugging whatever's inside here into all the places you're supposed to, right? So looking at our example, if I was trying to figure out what h of 5 is, I would have to make sure that 5 gets plugged in for the x on top as well as for the x on the bottom, and I would end up with 5/4. Okay, well, of course, the same thing needs to happen for h of x plus 1. You've got to make sure that you're plugging x plus 1 in on top as well as x plus 1 in the bottom for that x right there. So we will end up with what? X plus 1 over x, it looks like. And we could leave it like that, or if we wanted to, here's a situation where we have a single term in the denominator, so we could split that up. That would be the same thing as x over x plus 1 over x, which would be 1 plus 1 over x. Either way is fine.